Let's look at VSEPR theory, which stands for valence shell electron pair propulsion theory. So far, the structural formulas that we have drawn are two-dimensional. Both molecules are actually three-dimensional structures. Within these three-dimensional structures, the lone electron pairs repel each other, and they also repel bonded electron pairs. And finally, electron pairs in different bonds are going to repel each other. What VSEPR theory says is that molecules adjust their shapes so that the valence electron groups, or regions, are as far apart as possible. And what we will do is treat each double or triple bond as a separate electron region. So let's take a look at electron region geometries and molecular geometries. The simplest one is what's called a linear electron region geometry, where we have two electron regions on either side of the central angle. To get as far apart as possible, these are going to be 180 degrees apart. An example of this would be CO2. So this, if we were to do the Lewis structural diagram of this, has a total of 16 electrons. Let's go ahead and do a little bit of review as we do this. We're going to have first start off with the central atom and the two oxygens connected by single bonds. That's 4 electrons. Now we're going to fill the outer electrons, or fill the outer atoms with electrons. So we do that. At this point, we have used up 16 electrons. However, this central carbon still needs 4 more electrons. So we're going to share 2 of the oxygen lone pairs. And when that happens, they will be shared as a double bond. So our final structure ends up looking like this, with 2 electron regions around the central atom. In this case, the electron regions is this double bond and this double bond, so the angle ends up being 180 degrees if we're looking at the O to C to O angle. Now let's look at what happens if we have 3 electron regions around a central atom. In this case, they're going to be arranged in a plane where if we were to connect these outside electron regions, it looks like a triangle. It all lies in a plane, and each one of these angles is 120 degrees. So let's first look at sulfur trioxide. If we count the valence electrons, this is 24 valence electrons. So we're going to go ahead and connect the oxygen to the oxygens to the central sulfur atom by single bonds. Fill up the outside electrons with the remaining electrons that we have available. At this point, if you count, we have used a total of 24 electrons. However, sulfur still needs 2 more electrons to have a full octet. So we're going to share one of the oxygen double pairs, lone pairs, and we end up with a Lewis dot structure that looks like this. Now, the way we've drawn this, it makes it look like this angle here is 180, and each one of these is in 90. But what's going to happen is the electron pairs are going to repel each other, and it's going to be arranged around the central atom in the trigonal planar geometry. So more realistically, we would draw the molecule as looking like this. with the angle being 120 degrees. So this is your electron region geometry. It is trigonal planar. Your molecular geometry is the same thing, and I'm going to have to abbreviate here because I'm running out of room. It is also trigonal planar. Now let's take a look at another molecule here, ozone. And in this case, we're going to have 18 valence electrons to work with. One of the oxygens is going to go in the center, so we've used up 4 electrons so far. Let's fill up the outer ones. 6, 8, 10, 12, 14, 16. So we filled up the outer atoms. We still have 2 electrons left that we can use, so we're going to put that on the inside oxygen. Now we've used up 18. However, this oxygen still only has 6 valence electrons, so we're going to share one of these pairs to form a double bond. So now, when we redraw the Lewis structure, we redraw it like this. Now, the way we've drawn this, it looks like it's a linear molecule, but that's not the case, because a lone pair occupies space. So this lone pair is occupying space. It's like we took this drawing here, and we turned the top group into a lone pair, and the other 2 atoms remain. So when we go to over here to draw the molecular geometry, what we're going to have instead is something that looks much more like this. And let's finish putting on our lone pairs of electrons in the various locations. And there's all our lone pairs of electrons. I didn't draw this very well. What ends up happening is this angle here, the oxygen, oxygen, oxygen angle, is going to be very close to 120 degrees. But instead of 120 degrees, it actually ends up being 170. So we're going to say it's around 120 degrees. It's actually, in fact, always going to be slightly less than 120 degrees. And the reason is that this lone pair, because it is not trapped between 2 atoms, actually occupies more space than a bonded pair. So lone pairs take more space than bonded pairs. So lone pairs squeeze the other angles. And let's use a more scientific term. Lone pairs compress the other angles. Let's come back up here and look at the molecular geometry. When we look at the molecular geometry, we're only interested in the positions of the atoms. It's like this is an invisible force field up here that we don't see. So the shape of this is called bent triatomic. And what I'm going to do is just highlight the regions we actually see. That says bent triatomic. So let's come up here and we're going to highlight. And let's use a nice blue color. And so what we have is a bent triatomic. Bent triatomic.